seminar. We've got some guests from National Central University in Taiwan. They're each going to give a little bit of an overview of some things they're working on, and so we'll pause in between each if you have some questions for each of them. So we're going to start off with Professor Yu-Chieng Liou. We've got Professor Kao-Shen Chung and Wei-Yu Chang, and I've known these guys since 2008 when I first went to Taiwan, and now we're like a lot older and doing stuff together still, and it's really amazing. So as students, like, keep in touch, because you never know. We did a project together last year. It's been really awesome, and they've been great hosts for me, and it's wonderful to host them here in Madison. So thanks for being here, and take it away.
Okay.
Yeah.
Thank you. Okay, good afternoon, everyone. I'm Yu-Chieng from NCU. So the title of our talk would be the weather radar application and in mesoscale meteorology at NCU, and my part will be focused on the radar data retrieval, assimilation, and the application in analysis, and the QPF. QPF stands for quantitative precipitation forecast. Okay, first let me briefly introduce our laboratory. This is the number of our faculties, 3 of us, the number of students and assistants. And our major instrument include a C-band dual-pole radar on the top of our department building. Another one is an X-band dual-polarimetric mobile radar and the MRR probe. Okay, we are from Taiwan, so Taiwan is here, a small island. This is Asian continent, and this is the Pacific Ocean. Okay, if you zoom in, this is the Taiwan island. The capital city is here, Taipei City. And from north to south, we have the Central Mountain Range, with the peak height reaching almost 4,000 meters. And the size of this island is about 36,000 kilometers square, and we have about 24 million people living on this island. And two-thirds of the island is occupied by the mountains, so most of the people living along the western coastal area. Now, to give you an idea about the size of this island, the state of Maryland is about the same size, but with only 6.2 million people. How about the great state of Wisconsin? Almost 170,000 kilometers square. It's a big state, but less than 6 million people. So you can imagine the population density in Taiwan is very, very high. Okay, now this is currently the Taiwan ground-based radar network. Currently, we have 20 ground-based radar operated by the Central Weather Bureau, our university, the Air Force, the Taiwan International Airport, the National Lab. Another 2 is under construction, and 2 more are under plan. So considering the size of Taiwan, I would say the radar density is also very high. Okay, among those radars, the Taiwan International Airport radar was the very first Doppler radar installed in Taiwan back in 1987. And in that year, this radar observed the Typhoon Alex. And this observation was also mentioned in this textbook. It is said in the book, the Typhoon Alex observed by Taiwan Airport radar, the first to be observed thoroughly by a ground-based Doppler weather radar over the open ocean. Okay, we also our lab also operate a mobile radar called TIMA. It's an X-band dual-pole radar since 2008. And this picture shows we deploy the radar almost in many places in Taiwan. Okay, and those pictures is taken in South Korea. We send our radar to Chang to participate in the pre-experiment for the Pyeongchang Olympics. Okay, so this is just like the Enterprise in Star Trek. We boldly go where no radar has gone before. Okay, with those radars, we study, those are the major research topics. We study the severe weather, typhoon, frontal, severe afternoon thunderstorm, terrain effect, and rainfall process triggering mechanism, wind and zone retrieval, QPE, QPF, wind energy, and disaster prevention and reduction. Okay, now let me start to talk about my own research. I joined NCU about more than 20 years ago. In the first few years, I used the traditional dual Doppler analysis technique to analyze the weather system in Taiwan. Then I realized that the terrain in Taiwan is a big problem. I need to have some technique that can handle the terrain. So that's the reason I developed the system called Wisdom. So the retrieval compared to the traditional method, the retrieval three-dimensional wind can be recovered over terrain and along and near the radar baseline. And the retrieval three-dimensional wind by Wisdom can satisfy the vertical vorticity equation. So they can be directly used for vorticity partial analysis. This is very important. I will explain a little bit later. And the Wisdom can optimally combine the data from profiler, sounding, surface station, LiDAR, selected model output, and any number of radars. Okay, now this is one example. This is from the 2008 SOMAX. We have a Central Weather Bureau radar located here, and the NCA Expo radar is here, and we try to analyze the wind field within this area. So the radar baseline is from here to here. Okay, so the left panel is the result from Wisdom, so you can see the prevailing wind is coming from the southwest. Okay, the dashed line is the radar baseline. You can see the wind can be well recovered along the radar baseline. And this is from the traditional technique. So you can see there's no wind retrieval along the radar baseline, and the wind close to the baseline is very noisy. And the retrieved wind satisfies the vertical vorticity equation. So that means this equation will be satisfied using the Wisdom retrieved wind. So under this condition, we can compute the contribution coming from the vectoring, the stretching, and the tilting terms to the temporal change of the vertical vorticity. And the residual term will be very, very small. So this is one example from the idealized case. The left panel is the left-hand side of this equation, which is this term. And the right panel is the summation of the other three terms. So you can see that they are almost the same. So under this condition, we can compute the contribution from each one of these terms. And I already started to use Wisdom to analyze the weather system in Taiwan. For example, this is the retrieved wind field within the red of Taiwan rock. So in this case, you can see this updraft and the downdraft in the windward and the lee side of the Central Mountain Range. And the reflectivity starts to intensify when the wind reaching a small hill. And there's no bright band. So the area is very unstable in this region. And we found that the cross-barrier wind increased with height. And there's a wind speed maximum about the Central Mountain Range. And this picture can be explained by a shallow water model. Okay, and the Wisdom is also running operationally in Central Weather Bureau in Taiwan, and the NCDR in Taiwan. NCDR stands for National Center for Disaster Reduction, and also by KMA. And the users in university include NCU, National Taiwan University, Chinese Cultural University, and the National Defense University in Taiwan, also KAU and the PKAU in Korea, and the Nanjing University in China. Okay, right now I'm working on a high-resolution Wisdom. So the resolution will reach about 100 meters. So I'm thinking about doing the multiple LiDAR three-dimensional wind synthesis under clear sky. So the application of this work can be the real-time monitoring of the PBL evolution, the early warning of the afternoon thunderstorm, air pollution, diffusion, wind energy, aviation safety, and model verification. So this is one example. This is a true wind field from the model, and this is a dual LiDAR analysis. This is the Taipei Basin, and we are designing and planning a field experiment in the near future. This is LiDAR operated by the Central Weather Bureau. Okay, after Wisdom, I also designed a thermal retrieval scheme. It's called it's a terrain permitting, so it's called a TBTRS. So by thermal retrieval means we can use the multiple radar synthesize the three-dimensional wind to retrieve the three-dimensional pressure and the temperature perturbation in the space. And this was first proposed by Kao-Shen back in 1978. And this work was considered a landmark contribution in data assimilation in this book. However, in Kao-Shen's technique, a Poisson equation needs to be solved for the pressure over each horizontal plane. So if the mountain exists like in Taiwan, it will be very difficult to solve this Poisson equation over this plane, because you will see over your horizontal plane, you will see the data empty area here and there. So that will make the solution very, very difficult. So this, in the TPTRS, this is a grid system in TPTRS. So we only do the minimization for the grid point in the flow region. However, when we do the minimization, we need to classify all the grid points into the starting point, interior point, and end point. And based on those locations, we can write down the variational code. So this is one example from the idealized case. The left panel is from the model. So you can see over the mountain, we have the P plot and the T plot, the pressure and the temperature perturbations, and we have the wind. So by using the wind and the TPTRS, I can recover the P plot and the T plot showing here. So you can see they agree with the true very well. And this is real case from SOMAX IOP8. Okay, in this experiment, we have two central weather bureau SPL radar. One is here, another one is here, and the NCU radar is here. We also have a profiler and the soundings. So this is a radar reflectivity and the wind. The mountain is here, okay? And this is a retrieved pressure and the temperature perturbations. So by combining these two systems, we have a three-dimensional variables over complex terrain. And those variables include the UVW, P plot, T plot, rainwater, and the stormwater mixture ratio, and the QV. When we estimate QV, we assume when the radar reflectivity is greater than 10 dBz, then we assume the air parcel is saturated. Then we can estimate the QV. And then we can assimilate those variables into the model, and we found the model's spin-up time can be reduced. And the radar data from only two value scales are sufficient for improving the model QBF. Now, again, this is a real case from the SOMAX IOP8. This is the retrieved wind and the temperature pressure from Western and the TPTRS. And this is a 6-hour forecast accumulated rainfall. This is observation. This is a result from data assimilation. And you can see that the model is able to capture the rainfall pattern and the quantity very well. And this is a pure model simulation without doing DA, and the model cannot capture the rainfall. Okay, a few years ago, I also get the VTRAS system from NCAR. And the VTRAS is a 40-watt Doppler-radar retrieval system for high resolution and rapid update analysis. And in VTRAS, the Kao scale model is used as a constraint. After I got the VTRAS, I did two major modifications. The first one is I added the ice, because the original VTRAS only used the one-gram process. The second one is I add terrain by using the immersed boundary method, IBM. So the new VTRAS is called the IBM VTRAS. So this is a comparison between IBM VTRAS and the WRF. So this is the U, this is the W, the mountain is here, and this is the T plot and the P plot. However, IBM VTRAS can do something which is difficult for VTRAS, for WRF. It is a building scale simulation with the grid scale reaching 10 meters. So we put the 4 buildings inside IBM VTRAS. The winds coming from southwest, so you can see the wet flow behind the buildings. I think this simulation will be difficult for WRF. Okay, so I already started to use IBM VTRAS to study the rainfall mechanism in Taiwan. For example, this is a case back in 2008. The 24-hour accumulated rainfall is more than 200 millimeter. Okay, so for this case, the entire rainfall mechanism consists of 6 different stages, from the offshore to the central mountain range. The detail can be found in this paper published in 2020, and we found that the terrain and the evaporation play a major roles in determining the structure of the thermodynamic field. I also use IBVGS to study a heavy rainfall event in northern Taiwan back in 2014, and in this case included the surface heating, sea breeze, topographic blockage, cold pool storms merging. And this is a storm structure in Taipei Basin showing the local circulation that can support the maintenance of the convective system leading to the rainfall. And this work already published in 2021 in Chang and SJ. And I also compared Western and IBVGS. Okay, this is the wind field at 2 different heights. Fortunately, they are similar. Okay, otherwise I will be in trouble. Okay. Okay, my most recent work is I try to remove the vertical structure ambiguity in the retrieved thermodynamic field. And this work was already published earlier this year in Multiple Review, and this is the old problem since 1978. Now let me explain what is the problem we are dealing with. When we talk about the thermal retrieval, we start from 3 momentum equations. On the left-hand side, you can see there's a theta V0. It is a basic state of virtual potential temperature. It can be determined by Bristol sounding. The QR is the rainwater mixing ratio here. It can be estimated by the radar reflectivity. And those terms, they include UW. They are the 3-dimensional wind can be obtained by the multiple-Doppler-radar synthesis. So that means the left-hand side can be computed. Then by using the variational approach, we can solve for the 3-dimensional pipeline and the theta C plot on the right-hand side. Here the theta pipeline is the normalized pressure perturbation, and the theta C plot is the virtual cloud potential temperature perturbation. However, if you take a close look at the pipeline, you will find the pipeline has the form of the derivative. So that means if you find a solution for pipeline, that will make this equation satisfied. If you add any constant to pipeline, the result will still be a solution. So that means the solution is not unique. So this problem will also make the solution of theta C plot non-unique. However, we still need a unique solution. So usually what we did is that we remove the horizontal average. So the only unique solution we can obtain is the deviation of the pressure temperature perturbation from their horizontal average, shown by these 2 terms. However, what we want to know is the 3-dimensional pipeline and the theta C plot, but we only have their deviation. So that means we need to solve for the horizontal average of pipeline and the theta C plot. Previous studies suggest we can use aircraft, but we know it is not available in daily operation. And we can also use the radio sound, but the temporal resolution is still very low. Some scientists suggest we can add 1 more equation for the potential temperature, but I found we need to make too many assumptions for the microphysics process. So our approach is we use the equation of state and the 3rd momentum equation. So after that, we can perform a vertical integration from a ground station where we have an in situ temperature and the pressure observations. So this is the equation of state. It is coming from the P equals rho RT. Okay, and this is the 3rd momentum equation. And the reason we are using this equation because this equation directly links pipeline and theta C plot. Okay, you don't see the derivatives. Okay, now this is a result from a idealized case. So this is a true and a retrieved pipeline and the theta C plot horizontal average profile. So the solid line is true and the dashed line is the retrieval. So you see the retrieved result agree with the true very well. And then we can use this profile to correct the retrieved deviation. So this is a true pipeline, and this is a retrieved deviation from the horizontal average by the traditional thermal retrieval. And we can use the profile to correct this field. Now, this is the corrected pi plot. Okay, so we have a much higher SCC and a much lower room square error. Now, this is the theta C plot. So you can see that in the deviation, you see a positive value here, but actually it is negative. So after correction, the theta C plot becomes negative again. Okay, now this is from the real case, from SOMAX. The red line is the sound from the sounding, the blue line is from the vertical integration from the service station. Okay, so let me give you a very quick summary. So the data retrieval and the assimilation greatly extended the application of radar data. And my research included new methodology development and study of rainfall mechanism and the QBF. And we certainly look forward to the future cooperation between UW-Medicine and NCU. Okay, thank you. This is the team in Taiwan. Thank you.
Let's pause for a question, because I know there's some people in this room that have had a radar class. There's some that aren't, and I think one thing that really comes out of this is hopefully to see all the different applications of this beyond maybe what some of the traditional stuff that people have thought of when they look at radar reflectivity. Question on the nuts and bolts, the application of this, deploying the radars where people don't deploy radars. Any questions at the moment?
Maybe later?
Yeah, we'll revisit this back at the end. So if you think of one, go ahead and write it down. All right, who's up next? Wei-Yu? Go ahead.
Okay, good afternoon, everyone. So my name is Wei-Yu Chang. So I'd like to give you some very brief, introduce my the current research topic, my team. So first, we spend lots of time trying to understand the background environment condition and the kinetic characteristic of the mesoscale system over Taiwan. So we focusing on the a few campaigns. One is no COVID-21. Yes, YESR 2021, and of course the Kao 2022. But today I only give you very few examples of these two experiments. And also we are working on the convection storm identification and tracking them, and we want to understand the evolution of these convections from using radar data. And we also working with the Center Weather Bureau of Taiwan. We planning to have a dual wavelength radar. So we also developing some dual wavelength radar retrieval technique for the future application. I also do very fundamental study like quantitative precipitation estimation. So we have some results trying to improve the QPE due to the vertical caused by the vertical variation of microphysical process. We want to improve that. And this one is Taiwan also having a shipborne radar next summer. So we are working on the shipborne parametric radar data analysis tool because we want to compensate the ship motion if there's a ship motion. Ideally, the radar system should be able to compensate the ship motion, but if there's some remaining error from the ship motion, we want to see whether we can correct that. So that's about some. So this is the study we have been working on for a long time for the data quality. So this is a very dome attenuation correction. So most of people use radar data directly, even though especially expand they consider we have less issue due to the attenuation or the weather dome. But in this particular case in Taiwan, we have a WSR-8080 radar have a very pronounced weather dome effect. So we take this opportunity to take a look at how much weather dome effect we're going to have. So in this particular case, this is the very strong case 2017. And we have very strong score line past the radar side. And this is the quasi QVP profile. You can see there's a strong convection on top of radar. And the red lines represent the system bias. We use the self-consistent algorithm basically from dual measurement. We can check the reflectivity to see whether there's a systematic bias. Most of the time it's very stable, nearly constant. When there's a heavy rain around the radar, which is the blue line here, you can see there's a drop of the bias. This is not actually bias, this is the drop is caused by the rain on top of the radon that absorb the energy, that cause additional attenuation, and the result looks like a bias. So you can see once the reflectivity goes down, there's no rain on top radar, the bias value go back to the normal constant value. So this is a very good example of the very long effect. But we also found that the very long effect not always happen. For this case, it's a typhoon case. We have a heavy rain on top radar, but there's no very long effect. The bias remains constant value. This is because the very strong wind blow on the raindrop away from the radon. So turns out not only the heavy rain on top radar will cause the very long effect, the wind condition also would play some role in the very long effect. So on the right, we have a very simple polynomial equation that we are able to use the reflectivity around the radar to estimate the very long effect. And also, we can include the system bias. And this equation will need to consider the wind condition. The strong wind condition, it goes to the blue line. If the weak wind condition goes to the black line. So this is one of our study working on trying to improve the radar data quality. Another thing is we also working on the melting layer detection that we use idealized model from Roche V, ZER, and the Z, and then we want to calculate the height of the bright band. And in this process, we also try to derive the gradient of above the bright band and in the ice region, and below the bright band, the liquid phase region. We also can derive the characteristic of bright band, including the intensity of bright band and the thickness of bright band. So we can apply this model to different variables, so we can have a different characteristic from different formation variable. So this is our very preliminary study that we try to evaluate our algorithm against the sounding data. So this is the sounding data from 2017 to 2020. So you can see the algorithm detect the bright band between 3 to 5 kilometers. And the lowest one is around 2 kilometers actually. It shows very good consistency with the sounding data. So on the right is just an example of how our model looks like. The black line is the mean value of the profile from among the three variables. And the red line represents the fitting model we tried to derive. So this the peak value represents the location of the bright band. So for the case study for the mesoscale convective system, so this is the case from no COVID-21. This is a very typical Wei-Yu case. You can see lots of strong back building line echo past northern Taiwan, and so is the southern Taiwan. So we focus on one of the cases in northern Taiwan because we have additional sounding data, so we can have better thermodynamic retrieval product. So this is the wind retrieval result from Winston, professor that I just introduced earlier. So this is from 2 kilometers, and reflectivity and the shading reflectivity, the vector is the system relative wind from Winston. And you can see that there's a circulation around this is red band. We choose this guy, little guy, particularly because it passed northern Taiwan, and it's actually kind of dissipate due to the terrain effect. And so we kind of pick this one. So we want to understand how's the kinetic field change. So using the Winston result, we can calculate the divergence field, vorticity, and vertical velocity. And in this particular case, we can track the vorticity field, and this is possibly vorticity. And it shows that it's always the leading of the convection, and it shows very good correlation with the development of the convection. And we also take a look at the environment condition. So in this case, we have additional sounding, and then we kind of reorientate the wind direction to parallel to the line and perpendicular to the line. So we found that this particular backbuilding case, that this is a cross-section from dashed line here. So this is the backbuilding case. We see some new convection always generated from the back. And because the environment wind, upper level environment go downstream this direction, you can see the wind sounding data. And you can see the particle at the back downstream in this direction and form the stratiform region. And the convection is always showing on the upstream here. And this is the corresponding wind speed direction, wind speed field, and this is the vertical velocity field. You can see very strong vertical velocity developing in this direction on the left-hand side here. And then on the sterniform region, you can see less convection and show some downward motion that represent the characteristic of the sterniform region. So this is the case from no COVID-21. And the other case I want to share here is another interesting case, which is the winter precipitation in northern Taiwan. We're focusing on this particular small area in northeastern Taiwan. This is it's called Yilan. And this area is so interesting because it's surrounded by the high mountain here, and here is basically surrounded by the mountain. So only this area is lower and trapped by the mountain. And in the wintertime, there's a northeast wind coming from this direction. And usually we have quite lots of rainfall along the slope here. So in this particular case, we deploy TMR here, and also another small radar from NCU here, and also the ADAD radar here. So we have 3 radar systems. We can do better wind retrieval. So this is the particular time that we found that we have the most intense convection. It's different altitude, 1.5 kilometer, 2.5 kilometer, and most of the cases quite shallow in the wintertime in Taiwan. So we found that when the heavy precipitation happened here, it shows that we have very strong northeast cold convection air from the northeast to the southwest, and those air would accumulate along the mountain, the lower level here, and the mass accumulation will create a high pressure system. And turns out there's a barrier jet around this direction, and therefore the convection will be enhanced and propagate to the eastward. And this is the corresponding we call storm tracker. It's a small sounding system. So we can find that from the sounding system, we also found on the left-hand side here, more inside the mountain region, we have a cold convection signature. Outside, we have a warm convection system. So this is the case study we are working on, trying to understand the precipitation process. So for the convection storm identification, tracking, and evolution analysis, so we have developed our own storm tracking system. We call it SMART, Storm Motion Analysis by Radar Tracking. So using this is an example from 2008 storm activity data. So we use the SMART to track the convection like this. So we have a bunch of the radar data, and we can track the storm convection along the time. So we can not only have horizontal signature, but we also have the vertical signature. So we know the vertical structure of those particular convection. So we choose the single cell, relatively smaller size of convection with sufficient time, so we can actually get the evolution. So, and this is and each storm, because we have a vertical structure, so we are able to derive the vertical structure in terms of reflectivity, ZDP, ZDR, and the KDP. So here represent the time from 1 to 12 scan. So each scan, radar scan, we have one vertical profile. And this is the altitude from 0 to 10 kilometers. So because we have the storm, we have identified the storm, so we are able to calculate the mean profile of reflectivity and all the variable. And the peak line here represent if we vertically integrate the reflectivity, and the highest peak value we will consider that is the peak time of the convection. So any time before this timing, we'll consider developing stage. Any time after this time will be considered the dissipating stage. So we use reflectivity as our reference to define the most epic time of the convection. That's what the question looks like. So once we have that, we want to know the evolution of the convection. So this is the example from we classify the developing stage and the dissipating stage into 4 groups. So G1 and G2 represent the developing stage. So G2 is very close to the mature stage, and G1 is further away, it's more beginning time of the convection. And G3 is right past the mature stage, it's the beginning of the dissipating stage. And G4 is further away from the further dissipating, so that's the latest time. So we found that if we take a look at the maximum value, the tendency, we found that in the developing stage, the convection all showing that the maximum value of the reflectivity ZDP, ZDR, and the KDP, they show increase along the time. The time tendency is increasing. Especially G2 showed the highest tendency because it's very close to the epic time, the T0. All the variables show the same thing. We also take the vertical slope because the vertical slope of the all different variables showing that different microphysical characteristics. For example, if you can see the ZDR slope, if the vertical slope is positive, that means the bigger raindrop is lifted aloft by the vertical motion. So we found that, for example, in ZDR case, the G1, G2 always shows the vertical slope tendency is always positive. That means the convection, this updraft supporting the big raindrop aloft for longer time. And once it passes the mature stage, it starts to decrease. That means the big raindrop start to descend to the near the surface. So we also can see similar thing for the KDP, but not as strong as the ZDR. And for the ZHH, we don't see that much strong signature as the ZDR as well. So we found that this ZDR showing the most differentiated signature, showing that developing stage and the dissipating stage. So this is a potential possibility, a factor that we can use in the future that we can identify whether the system is developing or dissipating. And so this is and this part I'd like to show a little bit our new result about the dual retrieval technique. For this current work, we try to retrieve the liquid water content, and we use the co-locate X-band and K-band radar. Because we currently don't have the dual radar measurement yet from the Center Weather Bureau. The radar is building, it's not finished yet. But we managed to use the TMR, and we have the TMR look upward vertical, and we use the micro rain radar MR look also upward, so they can have a co-locate vertical pointing measurement. So by using this co-locate vertical measurement, we can have a dual retrieval. We can test our retrieval technique. So first, we try to use a very simple algorithm from Alice and Vivek 2011. So it's a very simple idea. Basically, try to calculate the mean differences from two different wavelengths, and the difference will be considered as attenuation. Then they just calculate the total attenuation and the mean reflectivity. Therefore, they can derive a relation between power law relationship between the attenuation and the reflectivity. So once they have these two coefficients, they can apply this coefficient back to the reflectivity. They can derive the attenuation at each range gate. But the disadvantage of this algorithm is the coefficient A and B here is showing very less reliability, and especially the coefficient A is each being only have one coefficient, so it doesn't really show the variability of DSD, and also showing that each gate should have different value of coefficient A. So we introduced a Z5 technique, which has been used a lot in the parametric radar community. The most recent application used the Z5 technique to retrieve the attenuation, and later on use the attenuation to estimate rainfall rate. And we use the same concept, but instead of retrieve the rainfall rate, we try to retrieve the coefficient A, because attenuation A is highly correlated to the liquid water content. So what we do is we replace this PIA is the path integrate attenuation, because in the conventional Z5 technique, you require the VDP measurement from the radar and need a coefficient alpha, and this alpha coefficient have a very big uncertainty because of the DSD variability. But in our particular case, because we are using co-locate measurement, so we can just directly derive the PIA. There's no assumption, just the differences between two radar, just the link to the PIA. So we can use this equation to derive the attenuation at each range gate. But another issue is we are choosing X-band and K-band. We actually, turns out we have an issue, is a mid-scattering curve issue, because in the mid-scale region, in this particular wavelengths, between 1.2 to 3.1 millimeter size of the raindrop, the K-band, which is the red line here, actually has higher value than the X-band, which is blue line here. This showing that the mid-scale resonance effect. So we need to correct that, otherwise we cannot get good PIA here. So we developed a very simple technique to correct the mid-scattering effect. So the way how we test is we test in a more idealized framework, which is the OC study. we have a simulation of the beam profile from the distributed data. We have long-term, more than 10 years of distributed, so we can simulate the X-band and K-band measurement, so we can test our technique. It turns out the technique, as we expected, the Z5 algorithm with a mid-scale correction, we can have very good correlation in both liquid water content retrieval and the radar estimate size variable. So this represents how much water content we have. This represents how big the raindrop we have, the mid size of raindrop. And then we apply the technique to the Tahoe data. So we don't have the airborne measurement, so we use SPO IHI data. So we use SPO IHI data and apply the DST retrieval technique, and we try to compare what we have from the co-locate TMR and MR measurement. So this is and when we compare the SPO retrieval and our dual wavelength retrieval technique, because the sampling issue and the time differences, we cannot really compare gain to gain and time to time. So we kind of compare statistically. So we try to see the overall characteristic of the retrieval technique. We found that, as we expect, the Z5 technique is showing the better consistency with the SPO measurement. And another good thing is for our technique here is, because the Z5, the old technique fit from Scott, Ellis, and Vivian 2011, the reflectivity itself estimate the attenuation directly and also use the attenuation to estimate the liquid water content. Therefore, the value is always normal change. So you can see with the increasing of reflectivity, they always show increasing of the liquid water content, so they don't show the variability. Like the SPO, you show that the IES and the liquid water content, they can change a lot due to the different microphysical process. Using the FIG technique, you cannot show that kind of variability, but with our technique, we are able to do that. So we believe that the new technique should perform better retrieval result and can reveal more microphysical characteristics. And for the QPs, I only show a very simple thing that we developed some new algorithm to estimate the KDP. Basically use the self-consistency technique to retrieve the KDP. And once we have those retrieved KDP, this retrieved KDP will have better performance compared to conventional derivative technique to derive the KDP. So we have a better resolution and better magnitude of the KDP. So once we apply this KDP to rainfall estimation, we have better result. So on the right-hand side is the real case. I believe we have 5 cases, several cases. And we found that the new technique, which is the blue and light blue line here, showing the lowest room square error in all-range intensity, and also the normalized mean bias is close to 0 in the different range intensity as well. So this is something really quite encouraging. But the story doesn't end here, because we still have big issue, especially when we have in Taiwan we have a lot of thermal blockage issue. And if the radar is very high, in this case it's around 700 meters, and in this particular area it's very next to close to radar, but because the high mountain here, the radar always overshooting a lot. So the radar measurement above this area is about over 1 kilometer already. So every time we perform the QPE, it's always underestimate. So this is I think it's 24 hours accumulation of rainfall. You can see the shading from radar showing underestimation only. The radar estimation only like 30 to 40 millimeter per hour, but the rain gauge data showing the circle here showing around 100. So that means the radar QPE underestimate about half. So we apply a vertical correction technique adopted from previous study, but we try to derive the vertical correction profile instead. Now we didn't do it for the entire domain. We tried to do it in the subdomain. We allow them can have variability, spatial variability. Then we can improve the accuracy along this area. So we can see all the numbers showing the improvement. This is the example showing that in Taiwan, we have very severe underestimation of the rainfall in this area. So this vertical correction technique is very important for us. Well, in this case, we improve the performance here, but we also overestimate here. So here, in this particular issue, we haven't really solved the problem. We only solve part of the issue. We have to deal with overestimate here. So that's also ongoing work. So for the shipborne radar analysis tool, we This is our research vessel. We are planning to put a radar here, so in the next year, so we are able to collect some data. For the shipborne radar, we need to, because the parametric radar ZDR is very required, the horizontal should be aligned very well. So we kind of worry about that. Our research vessel is really smaller, so less weight. So maybe there's some ship motion issue. So we managed to collect one ship motion data. So the ship will have roll and the pitch motion. And if we convert those roll and pitch to canting angle and elevation angle, you will see that in terms of canting angle will be -5 to 5 degree canting angle variation. For the elevation, we also have around minus and plus 5 degree of elevation. So this will cause the ZDR measurement some issue. So we develop our own technique and see if we can improve the result. So this is the simulation, again, because we don't have the shipborne radar yet. So this is the differences, because the shipborne motion, we have the difference in ZDR, the ZDR and the KDP, you will have this issue. And what we perform here is, in the future, we will need to input your current measurement of ZDR and the KDP, and your current measurement of elevation angle, and the canting angle, and your desired correction elevation angle. Then with this 4 variable, we will be able to calculate the correction value. We apply this correction value back. Yeah, that's it. That's about my research. Thank you.
I think a big take home here is radar-based estimation of rainfall is really hard. But this is really impressive to see. So do you guys have a quick question for you before we move on? Okay, thanks. All right, go ahead, Kao-Shen.
So good afternoon, everyone. This is Kao-Shen Chung, also from National Central University, Taiwan. And yeah, the third part of this talk, I'm going to talk about the stimulus prediction of weather, mainly focus on precipitation. Okay, here is one example showing that in terms of a QPF, quantitative precipitation forecast, the x-axis is log the time, y-axis is the forecast scale. You will notice that actually when we talk about numerical weather prediction model, usually they suffer from the spin up issues. So even though nowadays the resolution is getting higher and higher, models still encounter a certain period of time to pass the spin up issues. And then you will see that the forecast scale remains useful. Okay. In the meantime, we have to deal with if it is the severe weather, the heavy precipitation can occur in a short period of time. So what if there is it happens during the spin up time? Okay. So there are 2 ways to deal with that. One is Euler, the other one is Lagrangian. So I'm trying to combine these 2 information, or try to deal with the predictions of weather in this the so-called short-term forecast. So one way to doing that, like as I mentioned, the Lagrangian algorithm is that there is one nowcasting system called McGill algorithm for precipitation nowcasting using Lagrangian extrapolations. Since it is designed from Canada, so the abbreviation is called MAPLE. Okay. The idea is relatively easy. What radar observed in a certain period of time, you try to collect it, for example, within 30 minutes or even within 1 hour. Based on this image, you can try to estimate the motion field in the entire radar coverage. So you know how the precipitation or how the system moves, but it's more dedicated. It's more sophisticated because it's not only one motion vector to tell you how does the whole precipitation move. You have more details in different directions, or within one precipitation, you may have different directions to move. So once you decided how does the motion field looks like, then you can do the extrapolations later on. Let's say for 1 hour, 2 hours, or even more than 3 hours. Okay. When we apply this kind of ideas in Taiwan, since as Professor Liou just mentioned, we have a terrain located in the center of the Taiwan. So orographic effect become an important issue. When maple system apply in North America, in general, the performance of the nowcasting can up to 6 hours, which means that by just doing the extrapolation of the radar image or radar refractivities, it is capable of doing the nowcasting up to 6 hours. And one reason is because you don't have, if the system do not have a significant growth and decay, okay, that's an important thing. But when we try to apply this kind of ideas in Taiwan, first of all, this is the area is relatively small compared to North America, and also because there are mountainous orographic terrain effect in the center of the Taiwan. So we have no idea how well this kind of idea can be applied in this area. So I have done many different case studies, frontal system, typhoon. Okay, in general, maple system when you apply in Taiwan, it is able to do the nowcasting up to 2 hours. However, as the animation here shows here, you can see that the upper one is observation. The middle one is actually you just do the extrapolations. Because there are a lot of area you don't have a radar information, which means that when there's no precipitation, then you cannot estimate how does the motion field goes. So in fact, after 2 hours, through the animation, you can see that the typhoon structures, through the extrapolations, the deformation become more and more significant. Okay. So as I just mentioned, since you don't have enough information outside of a precipitation area, so this is one of the main reasons why you see the typhoon structure become deformed, okay, in time. So in the past, people always try to merge or hybrid two algorithms. One is the radar echo extrapolations with the numerical weather prediction, the product or the output of numerical weather predictions in terms of rainfall. Okay. But that kind of hybrid or that kind of merge highly depends on how well or how good is your numerical weather predictions to forecast the QPF. Sometimes when it is good, then actually you can combine these two algorithms or two techniques together to prolong your nowcasting time. But usually, numerical weather predictions encounter significant challenges that they can predict the precipitations, but sometimes either location is not correct or the time to occur or to generate precipitation is not correct. So if your numerical weather prediction cannot provide a good information, by hybrid the nowcasting from radar echo extrapolations with model simulation cannot guarantee you a good result. So my idea is that when I try to combine these two systems or these two algorithms, Maple plus Wolf model, actually I'm combine or hybrid the informations of wind, because compared to precipitations, usually the circulation of the weather system is more reliable from numerical model. Okay, so the lower panel shows that after I merge or provide additional information from WRF model, and it is the wind information instead of a precipitation or rainfall. You see that when we redo it or when we do the nowcasting again, first of all, that kind of a deformation problem is alleviated, okay? And then second of all, when we try to examine the performance of precipitations, okay, you see that in general, well, the first 3 hours probably is more similar to maple, but maple only. But later on, when we combine additional information from WRF, actually the maxima and the pattern of the heavy precipitation on surface is much more similar to what in reality. And of course, when we further examine the forecast scale in different threshold of the precipitation, accumulated rainfall, you will see that first of all, the improvement can up to 4 hours. And second of all, you can capture even more heavy precipitations compared to only by using simple radar echo extrapolations. And this kind of a study, I generalized this kind of result for 16 different tropical cyclones. Okay, and in general, we can have a improvement by combining maple and the WRF model. Okay, and recently we tried to further extend it, the nowcasting system. How to construct an ensemble nowcasting system? One example, the idea or why we have this kind of questions or idea is that by looking at the radar echo, you will notice that at low level, actually the system moves from northeast to southwest. On the other hand, when you go higher, you will notice that actually the system or the propagation of the precipitation system actually is from southwest to northeast. So in fact, when people applying the radar echo extrapolation, usually we use the maximal reflectivity, which means that the radar image has actually 3D, but we try to compact and project it all together and only pick up the maximal reflectivities in that column. So in fact, by this example, you will see that there remains an uncertainty of motion field at different levels. So because of that, so we came out of the idea that why not just use those uncertainties or those information, the different motion field at different level as the uncertainties, and then generate the ensemble nowcasting system. So the original 2D maple, actually they just pick up the composite maximal reflectivities in the past as just mentioned, and then estimate the motion field and then do the extrapolations. Now, when we construct ensemble nowcasting, we have to figure out how to add the perturbations based on these 2D maples. So as I just mentioned in the previous slide, those perturbations actually try to represent the uncertainty of the motion field at different levels, different height. So that is the idea to based on once you estimate the motion field from original maple, and then you try to add up the random perturbations based on those uncertainties, and then you can create a set of ensemble nowcasting. So when we try to apply to the, as Professor Wei-Yu just mentioned, the 2021, we have the winter field campaigns in northeast of Taiwan. So the left panel shows that the left panel shows the observations in November, and also there is another 2 case actually, as it was the field experiment back to last year, Tahoe, the international field campaign. One is in the end of May, the other one is early June. Okay, and then the second column just shows the result from single or deterministic nowcasting, which means 2D maple. Okay. Compared to what we generate the nowcasting, we use the QPFP is the probability product we just pick up the 30% of the result, and also the probability matching. Okay, you will see that in general, compared to the observations, these three different cases, they can capture the heavy precipitation a bit better than just the 2D maple. Okay, here in May and June, you have a heavy precipitation, one in the southwest of Taiwan, the other one is in the west coast of Taiwan. Okay, and then you see that 2D maple in general, they cannot capture this kind of a heavy rainfall well compared to observations. Once we apply the nowcasting, and here actually we generate around 100 members of a nowcasting system, and then use the probability product to represent the precipitations. And you will see that the maxima actually is much better compared to 2D maple. Still, it's a little bit underestimates to the reality. But on the other hand, you will see that the precipitation structures looks much more closer to the observations. So after introduce nowcasting, okay, let's assume that this is a time of spin up, and then right now we pass the spin up time, and then we move on the radar data assimilation versus numerical weather predictions. The upper conception model does show you that to realize or to deal with the convections and to deal with the entire precipitation system, except the convective and the stratiform precipitation, okay, you have to be also pay attention to the environment, the pre-storm environment, the cumulus cloud, etc. And also to understand what's going on in the entire precipitation system. Not only the rainfall is the issue, you have to know the dynamic wind, and also you have to know what's going on, or the whole structures of temperature and the humidity. The lower panel shows you that data assimilation, when we try to assimilate the most common observation from radar, Doppler wind, and refractivities. Result shows that compared to observation, the right two figures all show you that after data assimilation, the analysis can capture the pattern of observation well. This is exactly the assimilate both the Doppler wind and the refractivity by using two different microphysics schemes. Okay. But as I just mentioned, there are still some important information like the thermodynamic temperature and the humidity information. Whether without those information or with those information, how important is that? Okay. The methodology, the data assimilation system I use is ensemble common filter. I'm not going to talk about the detail of this. So just quickly show you that, assuming that your analysis also remains some uncertainties. Okay. By using data assimilations, you can have information coming from forecast. Also, you try to combine the information from the instruments. So, but keep in mind that all the observations also remain some uncertainties. So how to do the linear interpolation between observation and the forecast, or we call background information, okay? And then try to form the new analysis. This is the idea of, well, in general, this is the idea of data assimilations. By using ensemble, you are able to describe those arrows, we call the flow-dependent arrows in different cycles or different time. Okay, so here, Professor Yu-Chieng developed TPTRS, okay, a thermodynamic retrieval algorithm. So in fact, we are capable of understand the structures of precipitations, the three-dimensional temperature inside the precipitations. So here we show the precipitation information, and here we have the temperature. This is a cross-section of the temperature structures. And near the low level, you can see the cold perturbations, and in the mid-level or a bit higher level, you see the warm perturbations. Okay. and in the strong convection area and the stratiform area, it can also represent the structures of a vertical velocity. Here you see a more significant up to more than 5 meters per second of the upward motions in the strong convection area. And stratiform area, you see that relatively low, no matter upward or downward motions in this area. So it is capable of retrieve those thermodynamic information inside precipitation system. So what if we try to assimilate those pseudo observations to the data assimilation system? Okay, here's the result. We have designed a different experiment. We have to choose. This is the OC test or idealized case study. Okay, the truth and no DA, and only assimilating reflectivity, Doppler wind, assimilating both, or assimilate reflectivity and Doppler wind even longer, up to 2 hours. Compared to when we have additional information coming from thermodynamic, such as the temperature or humidity. It turns out that compared to the truth, you can notice that the optimal or the best performance actually is that when you provide the information of temperature and humidity. If you can provide both, or if you can assimilate the information even longer, the result will be the best. Okay. Because of that, or what we just present for TPTRS is try to provide the information or try to obtain the information inside precipitation system. But I also mentioned that the information nearby or in the surrounding area is also important, especially for water vapor information. So the question becomes, are we able to obtain the information of humidity from scanning radar? And the answer is yes. As Professor Wei-Yu just mentioned about the dual wavelength retrieval back to Alice and Big 2011, they used the S-band and the Ka band to retrieve the water vapor information nearby the precipitation, nearby the storm environment. Okay. So we try to apply these ideas into our data assimilation system. And here just to show you that this is the SPOCA, the location of the SPOCA. In fact, those information of the humidity actually is quite close to the radar location. Okay. It's all about 20 kilometers, within 20 kilometers, but those information provide you the vertical profile of the humidity nearby the storm. Okay. So the way to assimilate, since this is the original data looks like, and then when we try to apply the idea to assimilate those information, actually, we can, because it's quite close, so you can just think about, how about just do the average, and then assimilate those one single point, one single profile. Or from the previous study, they divided by 4 different quadrants and try to represent the vertical profile of the humidity in different directions. So we also follow up the same ways to assimilate one average humidity of the vertical profile of the humidity, or we try to assimilate the information in 4 different quadrants. And then result shows that if we are able to differentiate, well, because different directions or different area may have a different distribution of the vertical, different distribution of the humidity. So it turns out that the pink dashed line represent that assimilate Doppler wind, reflectivity, and vertical profile of the humidity with 4 different quadrants. Represent outperform the other different experiments. And this kind of improvement can up to 4 hours, a shortened forecast. And then, is that the only way we can try to retrieve or obtain the information of humidity from radar? The answer is that we have another ways to retrieve the humidity. Okay. For weather radar, most of the time, people doesn't, or radar meteorologists doesn't like to see the ground target because it generates the ground clusters when, and then you have to figure out how to remove those noise when they try to analyze the data of a radar. On the other hand, those ground targets actually help you to derive the radar-derived refractivities, and then it can help you to retrieve the near-surface humidity. Okay, and this kind of idea actually is compared to other theory or other principle of the radar meteorology. This idea is relatively new. Back to 1997, Professor Frederick Fabry in McGill University, he found this kind of features and then tried to do the retrieval algorithms to obtain the near surface information of humidity. Here's just one example to show you that in reflectivity, it is possible that since you don't have, before you see the precipitation system occurred, most of the time you don't see anything, means that there's no precipitations. But on the other hand, the right panel just show you that reflectivity can provide you the information near the surface all the time, and then also demonstrate these high temporal and spatial variabilities, no matter there's a weather precipitation system or not. Also, when you combine the information of land use and the refractivities, you can see that actually they can somehow represent or somehow differentiate the urban area and the rural area of the water vapor distributions near the surface. So this is kind of a very useful information. And then here we try to assimilate this information because for the dual wave length, it provides you the vertical profile of the humidity. For the radar-derived refractivities, those information actually is the 2D distribution near the surface. Okay. So we try to apply the idea and try to assimilate those information. Especially this is one of the radar-derived refractivities so far, one of the information that can provide both within and outside of the precipitation area. So our result shows that the upper panel's observation for 3 hours total accumulated rainfall, and then the lower one 6 hours, and then compares to only assimilate the Doppler wind and refractivities. When we can provide the information of near surface humidity from radar-derived refractivities, it sees that you see that the heavy precipitation can capture even better than only assimilating radar echo and the Doppler wind. And then from the FSS score, this is the forecast scale. We see that the blue line, the blue bar represents that you have the additional information coming from radar-derived refractivities. Okay, from the beginning to the up to 6 hours, you all see the improvement. Okay. So, well, last year we have for the Tahoe International Field Campaign. Actually, we have an opportunity to combine both radar-derived refractivities and also, although we don't have the dual wavelengths from S-band and the KF band, we do have a micro-pulse differential absorption LiDAR. This instrument can also provide us the information of the vertical profile of humidities. So actually, this is a good opportunity for us to combine these two information. One is the humidity in vertical, the other one is the humidity in the near surface. So we try to deal with the data last year, and then once we obtain all those information, and then we would like to assimilate both information into the data assimilation system. The last part, okay, here is I just quickly show you that dual polarization parameters, ZDR, okay, is one information can tell you the size of the droplet Okay, in the past, people try to the traditional way when they assimilate the dual pole parameters, they try to update the rain mixing ratio and number concentration. And the main reason is because this is the control variables and the prognostic variables in numerical weather prediction system. But these two variables actually did not directly represent the information of size. Okay, so our new algorithm or our new approach is that try to combine these two information to obtain the mean diameters. And the mean diameter actually can directly link to what radar observed of the ZDR to tell you what the size, whether it's big or whether it's small. Okay, so our new algorithms try to kind of convert the two information first to obtain a mean diameter, and then use that information to assimilate the information of ZDR from radar observations. And then the result shows us that when we use the new algorithm, actually, this is one example that originally, without data assimilation, you can already capture the precipitation, or your forecast of the precipitation is already relatively good. Okay, so what if we can go further to assimilate the dual Doppler parameters? Okay, the result is the lower panel. You see that we can further improve the QPF, especially when we apply the new idea of mean diameters to assimilate ZDR informations. The higher, in the probability forecast, we see the higher frequency to represent what's going on in this area to have heavy precipitations. Furthermore, when we examine the precipitation hourly, it turns out that this is QPE sums represent the reality on the surface, and then no data assimilation show you that each hour the hourly forecast of a precipitation, the amount remains similar. Okay, and even after you assimilate Doppler wind and refractivities, you still see that they compared to reality, it didn't have a similarity between a numerical model or the observations, even though their total amount of rainfall within 6 hours are quite similar. But the distribution in each hour actually is not that right. On the other hand, when you assimilate the dual parametric parameter ZDR by using the new algorithm we designed, actually you can see that the trend, at least the trend, I'm not talking about the total amount in each hour, but you see that the trend has similar situation as the reality on the surface precipitations. So this is one way we think that the new algorithm actually outperformed the original way people try to estimate dual pole parameters. Okay, so that's all I have so far. Thank you very much.
I want to thank you guys for taking all that time to show all the really interesting things that you're doing. There's a lot going on in the group related to radar, and I thank you all for coming. You know, I know this is the usual seminar time, we're past the hour, but it's much appreciated. Can you give another round of applause for all our speakers? So in recognition of the time, I would invite anyone who does have questions, no matter how broad or specific, to hang out and chat for a few minutes. Otherwise, thanks again for coming, and thanks for the introduction and all the work you're doing at the Radar Lab. Thank you.